Periodic continuous time signals can be expressed as an infinite sum of complex exponentials using the continuous time Fourier series. The adaptation for discrete time periodic signals is called the Dtfs, which stands for the discrete time Fourier series. The continuous time Fourier series allows us to express the periodic signal x of t as an infinite sum for n going from minus infinity to plus infinity of dn e to the power of j n omega 0 t, where omega 0 is of course the fundamental frequency of x of t, and the coefficients dn can be calculated by the formula 1 over t0, where t0 is the fundamental period of x of t, times the integral over one full length of the fundamental period of x of t times e to the power of minus jn omega 0 t dt. The discrete time Fourier series allows to express the discrete time function x of k as a sum which is not infinite, but instead is of length k0, where k0 is the fundamental period of the discrete time periodic signal. So similar to the integral over one full period here, we take a sum over one full period, which again we can start at any given point as long as the sum covers exactly one period of the signal. So x of k is equal to the sum of dn times e to the power of jn omega 0 k. So this is very similar to the expression for x of t using the CTFS. The main differences here are that we take a finite sum compared to an infinite sum, and the complex exponential is e to the power of j n omega 0 k instead of e to the power of j n omega 0 t. And the coefficients dn are given by 1 divided by k0 times the sum, again, of length k0 of x of k times e to the power of minus jn omega 0 k. Since we have a dt signal now, we can't take the integral over dt, but instead must calculate the sum. And the complex exponential again is e to the minus jn omega 0 k instead of e to the power of minus jn omega 0 t. Let's consider this example of a periodic discrete time signal x of k, which is 1 for all times k which by magnitude are less than n, and 0 for all times k between n plus 1 and k0 minus n minus 1, where k0 is the period of the signal. So again, x of k is equal to 1 for all values of k between minus n till n, and 0 otherwise, and has a period of k0. The formula for the Dtfs coefficients dn is given by 1 divided by k0 times the sum for one full period k0 of x of k times e to the power of minus jn omega 0 k. So here we could choose to take the sum starting at k equals minus n up until k equals k0 minus n minus 1. So that dn is equal to 1 over k0 times the sum for k equals minus n till plus n, which includes these samples here of x of k, which for those samples is equal to 1, times e to the power of minus j n omega 0 k, plus the sum for k equals n plus 1 up to k0 minus n minus 1, which includes these samples here, for which the signal x of k is equal to 0, which we have to multiply with the complex exponential e to the power of minus jn omega 0 k. Of course, the second sum doesn't contribute to dn, and we want to rewrite the first sum as 1 over k0 times the sum for k equals 0 to 2n of e to the power of minus jn omega 0 k. And in order for those two expressions to be equivalent, we have to multiply the entire sum with e to the power of j n omega 0 capital N. For the next step, we need to remember the formula for the geometric progression. It says that if we have a sum for k equals 0 to capital N of q to the power of k, this is equal to 1 minus q to the power of capital N plus 1 divided by 1 minus q. Using this formula, we can rewrite dn as equal to 1 divided by k0 times e to the power of jn omega 0 capital N times 1 minus e to the power of minus jn omega 0 of 2n plus 1 divided by 1 minus e to the power of minus jn omega 0. This is equal to 1 divided by k0 times e to the power of jn omega 0 capital N times e to the power of minus jn omega 0 to capital N plus 1 over 2 divided by e to the power of minus jn omega 0 half times e to the power of plus jn omega 0 to capital N plus 1 half minus e to the power of minus jn omega 0 to capital N plus 1 half divided by e to the power of jn omega 0 half minus e to the power of minus jn omega 0 half. Combining those three complex exponentials, we see that they're equal to 1. And using Euler's formula, these two exponentials yield a sinusoid of n omega 0 to n plus 1 half, and these two complex exponentials yield a sinusoid of n omega 0 half. So that dn is equal to 1 divided by k0 times the sine of 2n plus 1 half times small n omega 0 divided by sine of 1 half n omega 0. And keep in mind that omega 0 is equal to 2 pi divided by k0, so that we can write dn also as 1 divided by k0 times the sine of 2n plus 1 divided by k0 times n pi divided by the sine of n pi divided by k0. And plotting the coefficients dn for capital N equals 1 and k0 equals 10 yields these periodic coefficients dn, which have the same period 10 in the time domain and in the frequency domain.